Okay, again, welcome to today's digital classicist seminar. Today's invited speaker is Youssef Nader, who has a background in computer science and has recently used his abilities to solve some problems in ancient studies, as you will see during his talk. Youssef started his career at the Cairo University, where he did a bachelor's degree in computer engineering between 2015 and 2020. And after that, he moved to Berlin and studied data science at Freie Universität Berlin and completed his master's degree last year, so in 2022. And simultaneously, he worked as a software engineer, software developer, and even chief technical officer for several international companies. And now he is a member of the Berlin Bio-Robotics Group and is interested in interpretable machine learning, explainable AI, and neurosymbolic methods. And he is planning to start a PhD project soon, also at Freie Universität. And today we are very happy that he will talk to us about his work that has won him one of the prizes in the Vesuvian Challenge, which aims at making legible parts of the Herculaneum papyri, and which is, of course, at the center of our interest. So thank you for agreeing on short notice to show your work to us today, and the floor is yours.
Yeah, thank you so much for the invitation. It's really an honor to join you here today. Sharing, I would really love to share with you the exciting work of the past few months on the Vesuvius Challenge. I think we can skip the introduction. Maybe one more small piece of trivia to add. In the work interest is self-supervised learning, which I think is the most relevant part of today's talk. Looking at the scrolls at a glance and what the Vesuvius Challenge was all about, a little bit of history, was in the year 79 AD, Mount Vesuvius erupts and it buries the villa of Julius Caesar's father-in-law under hot mud and hot ashes and gases. And the villa contained very huge libraries. I think it contained one Greek library, which most of the work will be showing today is from, and it's theorized that there's an even bigger Latin library that is still buried underneath. And many years later, I think around the year 1700, one time a farmer was digging and he found something that didn't look quite like the other mud and rocks, and this was the first time the scrolls were discovered. And over the years, there have been several attempts at reading these scrolls, but as you can see in the middle image, they are not in the best state, buried under the hot mud, and it has been many years. They're very brittle, so they're pretty much carbonized. They're still intact, and we'll see that we're today able to read them, but touching them even is a very risky step, and they might just crumble. And a lot of the process or the attempts that try to read the scrolls before end up destroying some of the scrolls. So they're really tricky to work with, and they're in a really bad state. Some other stuff that were, or parts that were discovered in, or excavated from the villa were some detached fragments that were just like 2D fragments that fell off or detached. And these represent a big part of the movement to read the scrolls, because they were much easier to deal with. The step of unrolling was not present. So we have a scroll that is a rolled 3D object, and we eventually want to read it, and we want to be able to unroll this 3D object. And Professor Seals in the University of Kentucky pioneered a series of advances in this approach. So segmenting the scrolls is the process to separate the separate papyrus sheets, and we're able to scan the scrolls at a very high resolution in particle accelerators, and this results in a series of slices. If you think of it like a rolled pie, there are like series of 2D slices that you can see, and a single 2D slice would look something like this. So you see a lot of the sheets going around, and the process of segmentation, and this is where we get data that we use from, is we need to trace the individual sheets, the curves in this image, to say, yeah, this point and this point and this point, they all belong to the same sheet of papyrus that we want to read. And we need to do this also for all the subsequent slices. So in the next image, we need to define also this point is this point now, and this point is now this point. So this 3D point cloud creates a sheet of papyrus. And this process is fairly manual, but there has been a lot of automatic efforts to accelerate this. And this is where we basically get the data from. So this has already been done before the challenge. There has been some advances on this during the challenge, but this was one of the biggest breakthroughs that led to us being able to treat this as a machine learning problem. And this reduced the problem of having a very brittle 3D object that we can really touch or deal with, that we could virtually unwrap it and look at what is inside without actually touching it. And this is where the ink detection and the reading of the scrolls actually comes in. This process of flattening and unwrapping the scroll creates sort of a 3D image. We're working in a very high resolution that we have also the thickness of the sheet as I mentioned. And some of the advances that have been, or the work that has been done prior to the challenge, was taking some of the fragments and going through this process. Although we already do have it like in 2D, we can also scan it in a particle accelerator and like trace it's now just a single sheet, but we can still trace the individual slices, and we can reconstruct this into a 3D image. And since we can also use infrared imaging and look directly into where the ink and what's the writing on these fragments, we can have a ground truth that we can compare to, and we can train machine learning models. So in the image at the bottom, the machine learning model can take a very small part of this 3D image, like a small cube, and you feed this into the neural network. The neural network tries to see what's in there, and then it would say, yes, this part has some ink, or this part doesn't contain any ink. And because this, for example, this very small fragment, I think it was somewhere between 7,000 pixels and 7,000 pixels, it was unrealistic to give this directly all at once to the machine learning model. So we work with very small cubes out of this 3D volume, and we just iterate through all of them. So we keep asking the model, is there ink here? Is there ink here? Is there ink here? And eventually we get a full image of where the ink is and what the words are. So the way we do this with machine learning is we have this U-like shape of neural network. This U-like shape consists of mainly just two parts. There's a part that tries to look at the image and see, yeah, I think I see this kind of feature here. I think I see some of this feature here. I think I see some ink here. And it passes this information to a second part of the network that says, okay, there is ink here and there is ink here. Maybe I need to blend them a little bit and reconstruct this into a 2D image that we can look at and say, yeah, this is the ink. And at its heart, it's just a multiple output classification problem. So the network is trying to classify separate parts in the image or separate pixels, depending on what resolution you would go. Is there ink in this small green rectangle? Is there ink in this small green rectangle? And then it reassembles this individual predictions into a 2D image. And these advances were the catalyst of getting to the Vesuvius challenge. And there were two fronts, the ink detection and the segmentation that we talked about. And ex-CEO of GitHub and tech entrepreneur Nat Friedman reached out to Professor Brent Seals in Kentucky, and they pioneered the Vesuvius challenge with the purpose that we can push both fronts and we can actually get to reading the scrolls. And the Vesuvius challenge is actually made up of a series of challenges inside. So there were already two segmentation challenges that got the segmentation tool that is used to be really, really quick and very handy. There was the ink detection on Kaggle, which worked on the detached fragments. So the challenge contained one hidden fragment that was not public, and participants needed to create machine learning algorithms that work on the 2D detached fragments. And there was another challenge, which this was my first participation with the Vesuvius challenge, which is the ink follow-up prize. And the ink follow-up prize was sort of the bridge between the ink detection and the first letters. We had models that could see the ink in the 2D detached fragments, and they could follow the same process and see the ink. However, this advancement didn't translate to the scrolls. The scrolls which undergo the same process were pretty much dark when given to the model. And the ink follow-up prize was an open source brainstorming challenge of trying to see how can we go from here to there. The first letters, which was the main achievement of reading the first 10 letters from inside the scroll, and the fifth and grand prize that everyone is now looking at is reading 4 full paragraphs, continuous paragraphs of at least 140 letters each. So it's a big step from where we are. So the ink detection, the goal of the ink detection prize on Kaggle was, we have some fragments that we know for sure, this is the ink that's written, these are the letters, and this is where they are. And we had like 2D maps of a ground truth. And we wanted to train like the best models that we can with this limited amount of ground truth, and then try to see if we can see anything from inside the scroll. However, the models that were trained on these detached fragments would completely see nothing on the detached scroll, or have a very random signal that looking at there are no letters. And my idea for the ink detection follow-up prize was, what if we can do something before we show the model the Kaggle data? What if we can somehow learn some features from the data itself, try to get the same signal that we learned from the labels without using the labels, and then just train a little bit more with the ground truth, and then hope that we can now see the ink. And the goal is to familiarize the model with the data that it has not seen before. When the model sees this data, it's sort of surprised and doesn't see anything, and it's like, this is not something I've seen before, and it doesn't do any predictions or a very random predictions. So the idea was to use self-supervised learning to maybe try to learn some signal from the scrolls before we even try to show the model any ink. And this sort of stepped into the direction of seeing the ink. The models didn't entirely show the ink, but to understand a little more what the self-supervised approach is doing, if we have some part of the scroll like X that we have here, we can maybe change it in 2 different ways, give the model 2 different views. Maybe this one is rotated to the left, maybe this one is rotated and shifted a little bit. Maybe we can change the pixel intensities, sort of like doing Instagram filters on both of these 2 images. And then we feed both images to the model and see what the model sees, and we try to penalize the model if it sees 2 different images, right? If you look at the two images, you maybe for the ink, it's a little bit harder. For the scrolls, it's a little bit hard. But typically in self-supervised learning, if we see an image of a dog and the rotated image of the same dog, it's still the same image to us. So the intuition is that this proxy task should help the model learn these similarities from the data without using any labels. And this was the same for the ink models. So the ink model would take two variants of the 3D image from the scroll. We apply some augmentations that were used in Kaggle. We get some feature representation of what the model thinks it's seeing, a compression of the data from the scrolls. And then we just compare these two representations and we penalize the model. If you don't see these as the same, you should try to learn to see them as the same thing. And this, to some extent, helped the model familiarize itself a little bit with the scrolls. So now when it saw the scrolls, it wasn't, after fine-tuning on the Kaggle data, it wasn't completely surprised, but it was maybe 90% surprised. So it was still not enough signal to be able to read something. However, one segment came out, and the segmentation team is continuously working on segmenting the whole of the scrolls. One segment came out, and that's the first image on the left, which showed some hints of some letters. So there was a pi that was fairly clear. There was an O that is not so clear, and then maybe some signal above and below. But the surprising thing was that the signals seemed to be aligned in lines. So they seem to be all following the same shape and the same size and the same structure of lines, which gave some hope. And one of the other prizes that won the ink follow-up detection was, what if we fine-tune on whatever we see on the scrolls? So that I did that as well, and I created just manually in Photoshop. I just opened Photoshop and I thought, okay, I think I see a pi here, and I see an O, and I see something that looks like a tau or a T, and I just drew whatever I saw, and then I gave this to the model again, and I told the model, this is the ink, try to learn what the signal is and try to predict it. And to my surprise, from the first step of doing this, the model had a lot more signal than before. And it could see some letters and produce some predictions. And this was the first time it felt that this is actually the right direction to go. However, one big problem, which perhaps you can see here, is I only have had at the beginning maybe somewhere between like 5 and 8 letters, something like that. So it's a very, very small amount of data, and there was no way of really knowing whether the model is really just memorizing what I told the model to. So I told the model, yeah, there's ink here. So the model is just agreeing and saying, yeah, sure, there's ink here. Or is it like a signal that the model has actually learned? And overfitting is this peculiar problem of the model when they're at a certain critical size that sometimes is hard to know. They can just learn to memorize whatever you want to give them. So the model can just memorize, okay, you say there is ink here and you say there's ink here, I will just output this, and I don't have even to learn what the ink is, I just need to memorize these images. And for a very long time, I had like the step of some ink showed up and it looks really, really good, but it was not translating beyond this. The model was just, once trained on the data, it would just memorize and just say, yeah, this is what I see. On other segments of the scrolls, sees absolutely nothing and says, yeah, there is no other ink in the scrolls. And this began a journey of trying to debug and understand, okay, what's going wrong? Like, you're so close. And the first step to fighting the overfitting of the model was to go for a much smaller model. So typically models have many variables inside of them that learn how to represent whatever problem you're trying to solve. And the more parameters and more variables they have, the easier it is to just put everything in the parameters and just memorize. We don't need to do any learning. And after a lot of research of different neural network architectures, I found the Inception 3D, which we will talk about in a little bit. This was a good first step, but maybe not enough. So some other steps that helped fighting overfitting was to smooth the label and balancing the amount of data, positive and negative signal that the model is seeing. So it's not seeing everything as ink, or it's not seeing a very, very small amount of ink that it can just opt out of predicting, and trying to do as many good augmentations to the image and create as many variables, variations of the data that we have, so that the model has a harder time to remember the data that is being shown. And one crucial thing was to give the model some wiggle room to disagree and make some mistakes. So the Inception 3D is, or at the first glance, it was not something very special. It was just a neural network that is very deep. So it was this paper that came from Google, and it was very impressive that it was very deep and it was still very good at learning and extracting features. And then another paper came and said, well, Inception works very well in 2D images, let's do it in 3D images. And this is what I continue to use for a very long time. It's a lot harder to overfit because it's, I think, 1/3 of the size of the other models that were being used in Kaggle, or the smallest models that are being used in Kaggle. So it's really, really small compared to these models. And at the same time, it still achieves very similar performance. So it's very compact, but very efficient architecture for this problem. Now, the idea of label smoothing was we usually give the model ink or no ink. So it's like a binary signal of ones and zeros. And when the model misses something in the prediction, it's then penalized. You output a 0 or a 1, and it should have been the other. So it's like a very big gap that the model needs to breach, a very big mistake that it has made. And the idea was that I'm not really confident in the labeling I'm doing. First, like my handwriting isn't really that good with a mouse. It's unclear whether the model would be outputting the signal or just part of the signal. So maybe it sees like a letter C, but it should have been an O. So maybe it's just part of the curve and there's a part missing that it missed. And this part, when I'm trying to give the model some samples to train, I would then show it this model and tell it there is no ink, even though this is part that should have ink. And this process would be then introducing some false positives and false negatives to the model. Maybe I think there's ink there, or I just thought that maybe I should connect these 2 points when I was creating the label. However, this doesn't really contain any ink, so the model might start getting confused. It's seeing maybe a somewhat similar signal, but I'm telling it that this is not ink and this is ink. So it starts getting confused, and this reduces the performance. And the idea was that the model shouldn't really be very penalized for making a mistake. It should be okay to make a mistake or disagree with the labels. If you think there should be ink here and I'm telling you that there shouldn't, this is okay. If I'm telling you that this is ink and it's not ink, it's also okay. And this is the idea of high label smoothing. It replaces like these very hard labels on probabilities of this is a 0 and this is a 1 with much softer probabilities that are closer to that. Another factor of combating overfitting was trying to balance the data. So the scrolls in general are made of approximately 11 to 20% of ink, and the rest is just empty negative space. And if we're taking just the whole part, even if we have the whole amount of the data label, this gives the model a lot of samples that are saying, yeah, there's no ink here, there's no ink here, there's no ink here. And every once in a while, for the model, there is ink here. And what I observed is that sometimes this makes the model just lazy. So the model, there is a very big proportion of no ink. The model can just opt out to saying, well, there is no ink at all. And there is no reason to do all of this headache just for like 10% of the data. So a crucial part was trying to find the balance between the ink and the no ink data. And the way of doing this was to sample a small window around the letter. So where I'm seeing ink, this is going to be my data, but not just the letter that I am labeling, but a little bit all around it. And this window sort of creates a balance of the amount of data. Letters are usually between 500 pixels to 500 pixels or 5 micrometers. So taking maybe 256 pixels all around creates almost a 50-50% balance. And this helped create some balance for the models. The models that were trained also on just ink data were very excited, and they would just show ink everywhere. And this was also a very bad behavior. So perhaps now there's been a lot of talk about ink, so maybe we should mention what is ink. So and this was the first ink that we actually see from inside of the scrolls, but this was not discovered by any machine learning. Casey Hanmer was one of the participants in the challenge, and he spent a very long time just looking at the patterns that are showing in the data and just many hours looking at the scrolls. And as you can see, it's really hard to even know what we're looking at here. But if you look inside of the pie, you will find some sort of cracked patterns that sort of looks like there's been like an earthquake on the this part of the scroll, and there are like these fractured patterns that are going all around in the shape of the pie. And it's a lot thinner than the red line, so you would need to focus on the center of the spy, and you will see a little bit of fractures that seem like they make the letter pi. And these sort of patterns actually made a series of neighboring patterns. And back then, Casey published his findings and said, I think this is what makes ink inside of the scrolls. And then fast forward to now that we actually have like a large data set of the ink from inside of the scrolls, we find that this pattern does arise a lot inside of the scrolls. We usually in many areas that we see ink, we see this pattern if we zoom in and search in the volume. And the two very famous images that came out from the announcement, they were like labeled before even we could read them, that these are very dense with this pattern that we're not really good at reading, but it does have this pattern. And I, for a very long time, was asking myself, why does it work? Why does this approach of iterative fine-tuning of I label some data, I give it to the model, and it makes some predictions. Why is this working? Or why is it not working from just a single shot? So I showed the model some ink. It should be able to predict ink. It's the same, probably the same ink type that was used throughout the entire scroll. And the idea or the working hypothesis is that there is some distribution of this feature, whether it's the ink crackle or the cracked mud inside of the scrolls. And when you're looking from the Kaggle data, the distribution, the shape of this feature is very different than the scrolls. And then the fine-tuning is pushing this distribution a little bit into the direction of the scroll. So the first data that showed it was very likely at the very tail of that distribution, or very faintly resembled what the model saw on the Kaggle data. And then when we told the model, okay, this is also ink, it started to shift the distribution. Maybe it should be over here. Then you show it like a little bit more ink, and then the distribution shifts. And hopefully, once we reach a certain point, we would be able to read the majority of the scroll, give or take the damage that has been undergone. So this was the final submission that I made after a lot of iterations. And this also, I think, contains the first word in the third letter. And it was very incredible to see this image, because at one point, for example, I thought that this phi was a T. I would just label it as a T or a tau, and I would give it to the model. And the model would just disagree and say, well, this is not this label you're giving, and it should be a phi. And this is the word purple in the third line here, and there is some also maybe a little bit in legible words or characters, but this was the big finding where the papyrologists, when they saw these images, they were like, yeah, this is the word purple. And it took a very long process of evaluating this to make sure that we are on the right track and this is actually ink. This is something that was going on for maybe a month with the technical team. Is how do we make sure that the ink we're getting is not the ink we're just giving the model? Maybe we're just giving the model some sort of signal and the model is just learning to give us this signal back. But how can we be sure that this is ink? And there were like a few pointers after a lot of experiments that pointed that it's very, very, very unlikely that the model is just reacting and that it's actually seeing ink. So one of the biggest points was that we made the context that the model sees at a single point very, very small. So a letter is maybe 500 to 1,000 pixels by 1,000 pixels, really big. But what the model sees at any given moment is maybe 64 by 64. So the model creates the full shape of the letter through very independent series of predictions of these separate windows. But in the end, these separate windows make the shape of the letter and not something random or a chaotic signal. These independent predictions also line up in lines and make up words that have not been seen by the model before. The letter sequences, for example, and maybe some of the letters even have not been seen by the model before. There was one part which from the signal in the in the leftmost column, at the top there was this special character. If you're familiar with Greek, I personally wasn't, and I thought this was just a bug, like the model is doing something wrong, but yeah, this is fine. And then when the papyrologists saw this, they were like, I know this is the this special character, and it was a very promising sign that I personally do not know Greek, so I thought this was a mistake by the model, but the model was able to generalize to something it has completely never seen before. This is where I'm currently at least publicly. There is still this photo maybe came, I would say, a month now. So there are like more exciting photos hopefully to be released soon. But we could see from this image like sort of the difference between 1 month of progress from the last image, and the model was able to predict most of this without even seeing this before. So the model was just seeing this for the very first time. It was able to see all of this ink, and the third column was actually very, very clear. And there has been a lot of efforts in deciphering this. I don't think we have yet like a complete translation, but I think we have some words. So there's the word purple, and there's like the word music, I think somewhere in the second or third column. And there's an ongoing process of translating this both in open source community on the Discord channel of the challenge, and also the papyrologists for like official transcription. Yeah, I think this concludes the talk. These are, if you would like to check out the projects, whether the pre-training or self-supervised learning or the model and the Vesuvius first letters GitHub, this is where you can find them. And if you would like, if you have any questions, you can also always reach out on my email or my LinkedIn. And yeah, thank you for listening.